All right. Cool. So yeah, so we'll go ahead and get started in a minute. Yeah, and hopefully you can get that review material sent over, because it's kind of funny because this review material that we got here, we've already gone over a couple times today because a couple of professors didn't give material, so didn't want to go over this a third time. Yeah, thank you, Trent. All right, cool. Let me go ahead and download that really quick. One moment. There we go. All right. So I think if this will load, it should be good. All right, cool. All right. Well, so yeah, and then I apologize if I make a few mistakes because unfortunately I did not have time to prep with this sort of review material, but anyways, I'll do the whole introduction. My name is Michael, I'll be the tutor for this review session. This is the exam 2 review for Agbewali. And yeah, is there any questions in particular that you guys would like to go over from this review sheet? Or would you guys be okay with just starting at the top and working our way down?
I'm fine with starting going through it.
Okay, yeah, that sounds good. All right, let me go ahead. Yes, we are recording. All right, cool. So let's go ahead and start with number 1. So it says use implicit differentiation to find an equation of the tangent line to the curve x squared minus xy minus y squared is equal to 1, given the point 2, 1. All right, so I guess we can just jump straight in. Let me go ahead. I'm going to write the equation down here. So first, we're going to want to find the derivative, or dy dx, using implicit differentiation. And the way we're going to do that is just differentiate each term, and remember to use the chain rule with our y's. So for our first term, differentiating this, derivative of x squared should just be 2x. And then for this middle term here, we're actually going to have to use the product rule. So if we use the product rule on this middle term, what should we get?
Would it be y plus x to dy dx?
Yeah, it sounds good. Don't forget we do have a negative sign out here, so I'll put a negative and then parentheses. So y plus dy dx times x, like that. Yeah, that sounds about right. Yeah, we're here. We took the derivative of x and we just left with y. And the second one, we took the derivative of y and got that dy dx out, and we still have the x. All right, and then this last term, when we differentiate it, we're just going to get minus 2y, and then don't forget to multiply by the dy dx. And then one other thing that sometimes trips people up is on this other side, we have 1, and we're also taking the derivative of that. We have to differentiate every term, so we get a 0 over here instead of 1. Right, and then from here, it's just going to be some algebra to isolate for dy dx. First thing I'm going to do is distribute this negative sign in here, make this a minus y and a minus dy dx times x. And then from there, what I can do is I'm going to add y to both sides and subtract 2x from both sides to get the to isolate our dy dx's. So we'll have, what is that? Minus dy dx times x from this term, and then our minus 2y times dy dx this term. And then here, plus y minus y cancel out, and 2x minus 2x cancel out. So we'll just end up with y minus 2x on this side. All right, and then from there, we can go ahead and factor out a dy dx. And we'll get minus x minus 2y on the inside. And this is equal to y minus 2x. And then we can divide both sides by minus x minus 2y, like this. And that should leave us with our derivative. So we'll have dy dx is equal to y minus 2x over minus x minus 2y. And then another way you could write this, if you wanted to get rid of some of the negative signs, if you multiplied top and bottom by -1 to get rid of the negatives in the denominator, you could also rewrite this as what would that be? 2x minus y over x plus 2y. But it's not really a big difference. These two are both going to be the same. So any questions on how I got the derivative there? I went a little bit quick through that algebra, but any questions on that before we move on to getting the actual tangent line?
No.
Cool. All right. So then from here, let's see. So for the tangent line, we're going to need, so we have a point and we're going to need, so we have a point and we're also going to need a slope. We're going to take advantage of the line of the form y minus y1 is equal to m times x minus x1. I believe this is called point slope form. So we already have our point, and now all we need is a slope, and we have the equation for the derivative, so we can just plug in our point into our derivative, and that'll be our slope m at that point, and then we can just plug into this formula for the line, and we should have our tangent line. So from here, we'll plug in our point 2, 1 into our derivative. Doing so, we'll have 2 times 2 minus 1, all divided by 2, plus, let's see, 2 times 1. And then you could also plug it into this one as well with the other signs, but you should get the same thing. So then multiplying that out, we'll have 4 minus 1 over 2 plus 2, which is just 3/4. All right, so that should be our m. So now we can go ahead and plug this in here along with our point 2, 1. So we'll have y minus, and then our, I guess I should label these. This is x1, this is y1. So it'll be y minus 1 is equal to, let's see, 3/4 times x minus 2, just like that. And then from here, you could multiply this out and isolate for y and get slope-intercept form, but you don't really have to. I think this is a fine answer right here. So yeah, any questions on this one before we move on to number 2?
Nope, I'm good.
Perfect. All right. Let's see. I think, yeah, I should be able to do 2 over here, and I'll leave 1 up just for a little bit longer. So you have plenty of time to write that down. Let's see. So number 2 says, suppose f of 5 is 1, f prime of 5 is 6, g of 5 is -3, and g prime of 5 is 2. I'm going to find these following values. So A, it wants us to find f times g derivative evaluated at 5. All right, so right now we can't really plug anything in because we don't really have anything of the form that we're used to here. So what could we do here to maybe get this into a form that would be easier to plug stuff into?
Do we want to use the product rule?
Yeah, the product rule sounds great. Yeah. And sometimes the notation can be a little bit tricky, but we should just be doing a product rule here because we have a product of functions. So all we're going to do is do our product rule. So product rule states that if we have 2 functions being multiplied, their derivative is going to be f prime. In this case, we're not evaluating at x, we're evaluating at 5. So we'll just put f prime at 5 times the original function g evaluated at 5 plus, and then we'll have g prime at 5 times f of 5, like this. Yeah, this is just standard product rule stuff. And now it's going to be pretty easy to plug in because we've gotten it into a form of the stuff that we're given. So we can just plug in, all right, f prime of 5, that was 6. This is going to be 6 times g of 5 is -3 plus, and then g prime of 5 is going to be 2 times f of 5, which was 1. So this should just be 6 times -3 is -18 plus 2 is -16. Yeah, so -16 should be your answer for that one. So any questions on that one? If we move on to part B.
No.
Cool. All right, so let's do B. Shoot, that is not a very good B. Let me see if I can read that really quick. There we go. All right. So for part B, it's pretty similar, but this time it's going to be f over g prime evaluated at 5. So now in this case, instead of a product, we actually have a quotient. So instead of using the product rule, we're going to use the quotient rule, right? Where we can just say this is equal to, so we'll have the top function f prime evaluated at 5 times g of 5. And so it'll be similar to the product rule, except we'll have a minus sign in between here. So then minus g prime of 5 times f of 5, all divided by the bottom function squared. So we'll have g of 5 all squared like this. All right, and then from there, all we're going to do is plug in the constant numbers. So this should just be, let's see, f prime of 5 was 6 times -3 from g of 5, and then minus g prime of 5 is what, 2, and then f of 5 was 1, all divided by g of 5 squared. Let's see, and then g of 5 was -3, so -3 squared. All right, cool. So we'll have minus 18 minus 2, all divided by -3 squared is going to be positive 9. So this should just simplify to minus 20 over 9. All right, cool. So not too bad. C is going to be pretty similar to B. So if you guys feel good with B, I think it should be fine to evaluate C. Are you guys okay if we move on to D?
Yeah.
Yeah. All right, cool. So I think I just about have enough room to fit D in here, and then we'll have to clear the screen and move on to the next one. All right, so D is interesting. So it wants us to evaluate, so G over 2 plus F prime evaluated at 5. All right. Well, again here, we see we have a quotient, so it should just be quotient rule. So let's try to apply the quotient rule and see what happens. All right. So if we apply the quotient rule, the first term is going to be G prime of 5. Then we're going to be multiplying by the bottom function, which should just be, if I'm interpreting this correctly, 2 plus f prime of 5. Then minus, and then the next term should be, let's see, oh, not f prime of 5, my bad. Should be 2 just plus f of 5, I believe. F of 5. And then, oh no, my gosh, sorry about that. Just f of 5. There we go. And then the next term should just be, let's see, so we'll have, so if we take the derivative here, if we just think about, so what's the derivative of 2 plus f like this? This should just be, well, the 2 is going to go away because it's a constant, and then the derivative of f is just going to be f prime at whatever value, I guess x in this generic case. So in our case, that means that we should just get f prime of 5 here, times g of 5, and then all divided by this guy here squared. So we'll have 2 plus f of 5 all squared. All right, cool. So does the setup look good on this one? I'm a little bit rusty with this notation. So yeah, hopefully I did all that correctly.
It looks fine.
Cool. All right, so now we'll go ahead and now it's just a matter of plugging in numbers and evaluating. So we'll just have this is equal to, so g prime of 5, that's -3, times 2 plus f of 5 was 1. Let's see, and then minus, oh shoot, no, it was g of 5 that was -3. G prime of 5 is actually going to be 2. So let me go ahead and catch that really quick. All right, so that should just be 2, and then minus, so f prime of 5 is 6, and then g of 5, that's the -3, and then all divided by 2 plus, and then f of 5 should be 1, all squared, and this is equal to, I might run out of room, so then 2 plus 1, that's 3, times 2 is 6, and then we'll have minus 6 times -3, which is going to be plus 18, all divided by 2 plus 1 is 3 squared is 9. And then let's see, 18 plus 6, that's 24 over 9. And I don't think you can actually simplify that any further. So I think this should be your answer if I did that correctly. Fingers crossed. Yeah, I don't know if there's an answer key. Let me actually check really quick. I don't think, oh, there is. Okay. Shoot. Oh yeah, it looks like, oh yeah, no, you can simplify this. Yeah, my bad. Yeah, because this breaks up into 8 and 3, the bottom breaks up into 3 and 3, so this is just 8/3. Sorry about that. So yeah. But yeah, other than that, we should be good. So let me go ahead and stop my annotations. Any questions on number 2 before we move on to number 3?
Nope.
All right, cool. So, and then you guys are good if I clear this? Are you able to write everything down?
Yeah.
I'm good.
All right, cool. So let me go ahead and clear all of those. All right, so now I'll move on to number 3. So number 3 wants us to find the following limits. So the first one it gives us is the limit as x approaches 0 of sine 3x times sine 5x all over x squared. So if we were to just try and plug in 0 to this, right, we would get an indeterminate form because we'd get 0 times 0 over 0 squared, which we don't really know. It's going to be indeterminate form. So do you guys have any ideas on how we, like another way we could evaluate this limit as opposed to just plugging in?
I'm not too sure.
Yeah. So have you guys learned about L'Hopital's rule yet?
I believe so.
Yeah, I believe so as well.
Yeah, yeah, like L'Hopital's rule is when you have a limit of the form either infinity over infinity, or like when you have an indeterminate form for a limit of the form infinity over infinity, 0 over 0, it states that like if you have this case, the limit as x goes to whatever, I don't know, a, of f of x over g of x is equal to the limit as x approaches a of f prime of x over f prime, not f prime, g prime of x, like this. Right, like obviously if this limit exists, if this limit doesn't exist, then this limit doesn't exist, and etc. Yeah, so to use L'Hopital's rule, we'll be taking the derivative of the top and then also taking the derivative of the bottom. So kind of like the dream quotient rule, what we all wish the quotient rule could be. So yeah, I think a good way that there is definitely a few ways to solve this, but the first way that comes to my mind is just L'Hopital's rule. And it's going to be a little bit ugly, but it'll be okay. We'll just have to use some product rule. All right. So, oh, and also before I move on, so this looks familiar, right? Like you have actually learned this. Just wanted to double check.
Yeah, seeing it helps.
Okay, cool. Yeah, because if your president hasn't taught you this yet, probably wanted you to evaluate it some different way, but yeah, I'll assume that we're good to go with this. All right. So so this is gonna be the limit as x approaches 0 of, so we'll take the derivative of the top, and I'll do that to the side here. So d by dx of sine 3x times sine 5x. So for this, we're going to need to use the product rule. So we'll take the derivative of our first function. That should just be 3 times the cosine of 3x. And doing a little bit of not quotient rule, chain rule in my head there. Sine 5x plus, let's see, and then the next one, it'll be 5 times cosine 5x plus, not plus, times sine 3x. There we go. So that should be the derivative on the top. So let me go ahead and see if I can fit all that in. 3 times the cosine of 3x sine 5x plus 5 cosine 5x times the sine of 3x, all divided by, and then in our denominator, that derivative is a lot easier to evaluate. That's just going to be 2x. All right, and now unfortunately, you'll see now if we try and plug in x equals 0 into this, we'll still have an indeterminate form because the sine of 5 times 0, well, that's just 0. So this term here would just go to 0. And then the same thing would happen with the second term here because we have the sine of 3x and sine of 3 times 0 is just 0. So that term will go to 0. So we have 0 in the numerator. And then we still have the 0 in the denominator because we have the 2 times x. So unfortunately, we still have an indeterminate form. So we're going to have to apply L'Hopital's rule again. All right. So doing that, we'll get the limit as x approaches 0 of, so now we're going to have another product rule with this one, then we'll have another product rule with this term as well. So the first term, it's going to be, let's see. So we'll have 3 outside of, what's that, minus 3 times the sine of 3x times sine 5x plus, let's see, the next term is going to be 5 cosine 5x cosine 3x. That looks like an alpha. Let me rewrite that x really quick. All right, so that's going to be our first term, remembering the 3 that's on the outside. And then the next one is going to be, let's see, it's going to be really bad. I'll just put it down here. So plus, so it'll be 5 times, what is that, minus 5 sine 5x times the sine of 3x plus 3 cosine 3x times the cosine. Man, why are all my x's alphas today? Sorry about that. Times the sine of, or no, cosine 5x. Yeah, the other one's cosine 5x. Whew, all right. And then I think I need one more parenthesis. Yes, all right. And then all this, that whole big sum is all divided by, and in the denominator, we just get 2. And this is super nice, right? Because now we know that we can actually plug in because our denominator is going to be non-zero, which is just a constant 2. All right, so now plugging in. So plugging in 0 into this first term, we'll have, so the sine of 3 times 0, that's just going to be 0. So this first term goes to 0. And the second term here, the 5 times cosine 5x times cosine 3x, the cosine of 5 times 0, or the cosine of 0, is going to be 1. So this is going to be 1, and this is also going to be 1. So we'll just be left with 5 here. So we'll have 5. And then the next term here, we have, again, 2 sines. So this is going to go to 0. And then for the last term here, we have 3 cosine 3x times the cosine 5x. Remember these, like the cosine 3 times 0 is still 1. This one's also 1. So we'll have plus 3. And this is all divided by 2. All right, and then if I've done my arithmetic correctly, this should turn out to be 8 over 2, which is just 4. So fingers crossed that matches up with the answer key, because I really don't want to do those product rules again. So let's take a look. Shoot, it looks like the answer was supposed to be 15. Yeah. Strange. Yeah, so probably made a mistake with my, oh, you know what I did? I forgot about the outside. Let me go ahead and do this. I forgot about these coefficients I left on the outside. So this 3 actually needs to be distributed back in. So I should have probably just done that all in one step, but apologize. Looks like I forgot about that. Yeah. So with the first term, it's actually minus 9 times the sine, but that term still goes away. But then the second term, we have 5 times 3. It's not just 5. So this turns out to be 15. And then the bottom term down here, this minus 5 times the 2 sine functions, that one goes away. But then multiplying the 5 times the 3 gives us another 15. So instead of 5 plus 3, we actually end up with 15 plus 15 over 2, which is 30 over 2, which gives the desired 15. Yeah, so had a small little algebra hiccup there, but yeah, so pretty nasty L'Hopital's rule, but Yeah, so any questions on this one before we move on to the next one?
I'm good.
All right. Oh yeah, and I should have labeled this. This is I'll write this over here. 3i. All right, and then so for the next one, I will do the second one over here. So the second one wants us to evaluate the limit as x goes to 0 of cosecant x times the sine of x. Let's see. Well, right now, it's actually not very easy to even plug things in because I wouldn't say it's the most intuitive. I'd say most people don't really remember what cosecant, what the values of that are. So I'd say the first step that I would go for here is move this cosecant to the denominator and make it a sine. So I would say this is equal to the limit as x approaches 0. So alpha approaches 0 apparently. X approaches 0 of sine of the sine of x, all divided by sine x. But then from here, we notice we're going to have a problem because if we plug in 0 up here, we'll get sine of the sine of 0. Well, sine of 0 is just 0, and again, sine of 0 is 0 as well. And then in the denominator, we'll have 0 as well. So we'll have 0 over 0 in determinate form. So what could we do here to evaluate this limit or make this limit a little bit easier to evaluate?
Could we use the chain rule in the numerator?
What do you mean by chain rule?
Like f of g of x.
Let's see. So f of g of x, so like the limit chain rule?
Yeah.
Yeah, shoot. Let's see. If you could refresh my memory on the I forget how exactly the formula for that goes. I don't know if there's a certain formula with that. Yeah, I don't know if you have something like that.
I believe it was f prime g of x times g prime of x.
Oh, yeah, you're jumping way ahead of me. Yeah, so you want to use L'Hopital's rule, right?
Yeah.
Yeah. Yeah, so we're gonna use L'Hopital's rule and then we're gonna evaluate the derivative in the top using the chain rule. Yes, exactly. I was like, wait, hold on, because I think there is like some weird rule with limits and the chain rule, but yeah, here we can just use L'Hopital's rule and take the derivative top and bottom, then it should be good to go. All right. So for that, using let's see, L'Hopital, let's see. Hopefully I spelled that right. L'Hopital's rule. We're going to get the limit as x approaches 0. We'll take the derivative of the top, which, like you were saying before, when we have a composite function, I guess in this case it's kind of unique because we actually have f of x, and when you take the derivative of this is going to just be f prime evaluated at our original function times the derivative of the inside. All right, so first thing, we'll take the derivative of our outside function in the numerator, which is going to be sine x. So the derivative of sine is cosine. And we keep our input the same, keep this sine x input the same. And then we multiply by the derivative of this inside sine function, which is cosine. And then denominator, super easy, derivative of sine, just cosine. And you'll notice here that we actually have cosine x over cosine x, and those can just cancel out because if you were to plug in 0 into cosine, you get 1, so we don't have any domain issues there, so we can go ahead and cancel that out. So this limit just simplifies to the limit as x goes to 0 of cosine of the sine of x. All right, and then so what's this limit going to be?
Would be 1.
Yeah, it's just going to be 1 because if we plug in 0 into the sign, we get 0, and the cosine of 0 is 1. All right, cool. So then as long as I've done that correctly, hopefully the answer should match up. Yes, 1. All right, cool. So any questions on that one before we move on to 3?
No, I'm good.
All right, cool. And then do you guys have everything written down? Good to clear?
Yeah, I'm good.
All right. Cool. Go ahead and clear those, and we can move on to 3. All right. So for this, it wants us to evaluate the limit as x approaches 2 of sine of x minus 2 all divided by x squared plus 2x minus 8. And it may not look like an indeterminate form at first, but you'll see that if we were to plug in 2, we're going to get 0 in the numerator. 2 minus 2 is 0, sine 0, 0. And then in the denominator, we'll get 2 squared plus 2 times 2 minus 8, which is 4 plus 4 minus 8, which is again 0. So again, we have this 0 over 0 indeterminate form. And for this, it's going to be similar to the other problems. We're just going to go ahead and move on with L'Hopital's rule. Sometimes there's some tricks you can use to cancel some stuff out, or some other algebra tools you can use. But for these, L'Hopital's rule seems most appropriate. So coming down here, we'll have the limit as x approaches 2. Taking the derivative of the top, we'll have cosine of this input stays the same, and then we multiply by the derivative of the inside, which in this case is actually just going to be 1. And then in our denominator, taking the derivative of that, we'll get 2x plus 2. All right, and now from here, we should just be good to plug in. So plugging in 2 into our numerator, we get cosine of 2 minus 2, and then I'll just get rid of the 1 because 1 times anything is just that thing. All divided by 2 times 2 plus 2, which is just going to be cosine of 0 is 1, like we were saying before. All divided by 2 times 2 is 4, plus 2, that's going to be 6. So 1/6. And I'm pretty sure I saw in the answer key that it was 1/6. So yeah, that one not too bad, especially compared to that first one with all the product rules. So yeah, any questions on that before we move on to number 4?
Nope.
Perfect. All right, so I'll go ahead and leave that up for a little bit, and we can move on to 4, doing some derivatives. Let me get a little better 4 there. So for 4, the first one, it wants us to differentiate. So our function is f of t is equal to t times e to the t times the cotangent of t. All right, interesting. So for this, there's a couple different ways we can go about it. Do you guys have any preference on which, I guess, yeah, because we know we have a product of functions, right? We have a product of 3 functions. So the way I typically like to go about differentiating a product of 3 functions is either put parentheses around the first 2 or put parentheses around the second 2. So do you guys have any preference on which one we do that for?
I don't.
No? All right. Well, I'll just do the first 2 because it seems most intuitive. So now putting parentheses around the first one, I'll put a multiplication sign here. This is going to be our f of t, and this is going to be our g of t. For our product rule formula, where it's going to be f prime of t times g of t plus g prime of t times f of t. So we'll do this. So f prime of t should just be, but now if you look at f of t, this is another product of functions. So in our product rule definition, the first term is going to be f prime of t. So we'll have f prime of t, g of t plus g prime of t times f of t. So our f prime of t, we're going to have to do another product rule. So it's kind of like nested product rule. So I'll do a quick aside. F prime of t is just going to be, with our definition, I guess I'll kind of, you know what I should do instead? Let me get rid of all these f's and replace them with h's instead. Just so you don't get confused with f of t and the original. So let me go back to here. So I'll just put h of t, h prime of t, and h of t here. So I'll define this to be h of t instead of f of t. So we have a different letter there. All right, so h prime of t, we're just going to use product rule for this. So it'll be e to the t plus t times e to the t. So yeah, the first one we took the derivative, t went away, and then the second one took the derivative of e to the t, get the same thing, just multiplied by the original t. All right, so that's going to be our h prime of t for this. So we'll have e to the t plus t times e to the t, all times our g of t, which is cotangent of t, plus, and then g prime of t. Can anyone tell me what the derivative of cotangent is? All right, any ideas?
I'm not sure.
Yeah. So I guess an easier question would be, do you guys know what the derivative of tangent is? This is kind of one you have to memorize. There is kind of a nice proof for it. I don't know if your professor went over it, but yeah, we definitely won't have time for that. So yeah, I'll just have to tell you what it is. So any takers on tangent t?
Would it be cotangent t?
Not quite. Yeah, so if you were to evaluate this, this would actually be secant squared t. There's a couple different ways to prove this. You could do some implicit differentiation. I think there's one way you can do it like that, or you could do a quotient rule where you do d by dt of sine t over cosine t. Like if you forget what the derivative of tangent is, you could always just do a quotient rule like this. And if you do evaluate this quotient rule, you'd get, let's see, let me speed through this really quick. Cosine t times cosine t minus, let's see, we'll have cosine t times minus cosine t, all divided by cosine squared t. And then in the numerator, we'll have cosine squared plus, oh shoot, I put too many cosines. Yeah, it'll be, the second term will be sines. So it'll be, yeah, minus sine t times sine t, and then the negatives will cancel out and you'll get cosine squared plus sine squared. So this is just going to go to 1, and then we get the secant squared t. So the derivative of tangent secant squared t, and the way I like to think about it is if you know the derivative of tangent t is secant squared t, then cotangent, it's going to be kind of similar, but a little bit different. So the derivative of cotangent t, if you were to go through the whole process again, you would end up getting minus cosecant squared t. So it's kind of like it's the other inverse trig function with sine and cosine, it's squared, and then you also have to flip the sign. So yeah, hopefully that helped more than confuse, but yeah, it's probably just another one of the ones that you have to memorize. I don't know if your professor gives you a sheet of derivatives for your exam, but yeah. So g prime of t here, the derivative of cotangent t should just be cosecant t. Not cosecant t, minus cosecant squared t. Sorry about that. Yeah, and then we'll multiply by original h of t, which was t times e to the t. So yeah, and then from here, you could go ahead and simplify this down a little bit, multiply this out, but I don't think there's too much big simplification you could do here. So I think this is a fine answer for f prime of t. So yeah, I think we should be good to stop here for that one. Any questions on number 4i? Or I guess number 4.1 in Roman numerals.
No.
All right, cool. So now we can go ahead and move on to number 2. Shoot, on the edge of my pad here. So number 2, it wants us to differentiate y is equal to 2 secant x minus cosecant x. So to differentiate this, we're going to need to know some more trig integrals and, well, not trig integrals, trig derivatives, sorry about that. So we need to know what the derivative of secant is, and we need to know what the derivative of cosecant is. So do you guys know what the derivative of secant and cosecant are? No, and it's totally okay if you don't either.
I'm not too sure.
Yeah. So with these, what it's going to end up being, so for secant, it's going to end up being secant times tangent. And for cosecant, it's going to end up being minus cosecant times cotangent, like this. And the way, like if you're on your exam and you get to this and you forget about it, a way you can do it is you can say, well, this is just going to be 1 over cosine x, and then you can do another quotient rule here. And if you do the quotient rule and simplify it, you should end up with this in the end. So yeah, so you can either memorize it or you could do this derivative instead. So yeah, so now from here, with these in mind, this shouldn't be too bad to evaluate at all. So y prime should just be 2, and then the derivative of secant, we just said it was secant times tangent. So secant x, tangent x, put some parentheses around those. Shoot, let me rewrite that as c. So we'll have secant x times tangent x. And then, so for the cosecant x, we'll have a minus sign out here, so the negatives will actually cancel, and we should just get plus cosecant x times, not tangent, cotangent. Bad. All right, cool. And then that should be your answer for that one. I actually didn't check my answer on the other one, so I'm gonna do that really quick. And then while I'm doing that, do you guys have any questions on these ones? Or I guess on number 2? Cool.
I don't have any questions. Thank you.
Oh, all right. Yeah, and then one of the, I didn't mention it, but with the cosecant, you can do a similar thing where you rewrite cosecant as 1 over sine to evaluate this one as well. But anyways, if there's no questions, I think I might just barely have enough room to do number 3 in the middle here. So for 3, it wants to find the derivative, or y is equal to x times inverse secant of x cubed. All right, so for this, it's going to be another product rule. So we'll have, so y prime should be equal to, so we'll do the easy one first. We'll evaluate, so the derivative of just x is just going to be 1. So the first term should just be inverse secant of x cubed. And then plus, so we'll have, now we need to differentiate the second term, which is going to be the trouble. So give me 1 second. So for the then for these inverse trig functions as well, there's also proofs. I think it's actually the inverse trig functions that you do implicit differentiation to prove them. I think what you do is you say, okay, well, y is equal to inverse secant of x, and then what you would do is take the secant of both sides, say secant y is equal to x, and then from here take the derivative of both sides and isolate dy dx and do some more manipulation there. But if you were to do that for secant here, you'd get the derivative of inverse secant of x is just going to be 1 over x times square root x squared minus 1, like this. Yeah, I don't exactly know any good ways to memorize this. I'm trying to think. I don't know of any like mnemonics or anything, because there's a few different ones. There's ones for all the inverse trig functions, like the derivative of inverse tangent is 1 over 1 plus x squared, and I think like arcsines 1 over root 1 minus x squared. So yeah, so these are just ones that kind of have to memorize. You could technically derive it on the fly in your exam using the implicit differentiation, but probably be good to just memorize those so you don't have to worry about that too much. All right, so now we have to apply that here, and we also have to do a chain rule. So it should be interesting. So if we're just differentiating inverse secant of x, right, we're going to have x squared and this x here. But in this case, we actually have x cubed. So we're going to plug in x cubed into where these x's should be. So we'll have, so this, the derivative of this should just be, well, of the next part, 1 over, we'll have x cubed, and then square root x cubed squared minus 1. And then we're going to multiply by the derivative of our inner function because of the chain rule. And the derivative of our inner function is going to be 3x squared, like that. All right, so that was definitely a lot for the inverse secant part. So any questions on that before I do some simplifying and finish it up? Let me write that just a little better. All right, I'm going to take your silence as a no. So then from here, what we can do, it's actually pretty nice. We can cancel out 2 of the x's in the denominator here. We can cancel out this x squared up here. And we'll have y prime is equal to inverse secant of x cubed plus 1 over x times the square root. X cubed squared, we're going to multiply our exponents because it's cubed then to another power. It's not times x squared, it's to the power squared. So we're going to multiply 3 times 2, and we'll get x to the 6 minus 1. Just like that. And then that should be your answer for that one. All right, so we have about 40 minutes left. Let me go ahead and double check, make sure this is correct. Oh, shoot, it looks like, I think there may actually be, it looks like they didn't bother simplifying it. I'm wondering if that's a typo or did I make a mistake here? Because they put the answer as 3x to the 3rd power. Oh, and then I forgot the 3, my bad. Let me put that 3 there. So we'll have a 3 here. And it looks like we ended up with x cubed. I think that might just be a typo. So yeah, it looks like they didn't bother even simplifying the x cubed and the x squared. So it was fine to think like that. But I believe that's just a typo with the x cubed, because when you do the chain rule, you have to subtract 1 off that exponent. So yeah, it should just be this. Because in that case, that's perfectly fine answer. All right. Yeah, and then so what I was saying, so we're definitely not going to have time to get through everything. So you guys should, there's no problems in particular that you want to go over, because if not, then I'll probably want to think about moving on to and getting some of these related rate problems.
You can move on to 5 if he's okay with it.
Yeah, I'd be fine with that.
Yeah, like these other ones, it's just going to be some more like trig functions. Like number 8's kind of sneaky because it's 2 to the 40th, but it's actually just a constant, so you're just deriving a constant, so it shouldn't be too bad there. 10 is just some more chain rule, and then 11's just some quotient rule, that sort of thing. And then 12 is a little bit interesting because you have to do some like natural log stuff, but it shouldn't be too bad. All right, so then if we have time, I think I might come back and do 12 on number 4. But yeah, for now, we'll go ahead and do number 5. So you guys okay if I clear everything?
Yeah.
Cool. Let's go ahead and clear those. I'll switch colors and let's do number 5. So number 5, the edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube. All right, so let me go ahead. Actually, I don't even think we'll need to, we may need to draw the cube, but I think for now we don't need to. So if we know that the edge is 30 centimeters with this possible error, we know that an edge, I guess I'll say S because E is kind of like already a number. So I'll just say like S for a side is going to be 30 plus or minus 0.1 centimeters, kind of like that. So that's going to be a side length. All right, so do you guys have any ideas on how we could start off by getting the maximum possible error?
I'm not sure.
What'd you say? Sorry.
I don't have an idea either.
Yeah. Let's see. So to estimate the maximum possible error. Yeah, this is one where it's definitely wish I would have had more time to prep. So I'm pretty sure there's a formula you can use for this. So I'm trying to remember exactly what it is for the, you guys, would you guys happen to have any like notes on formulas for maximum possible error or like relative error, percentage error, anything like that?
I do not.
Give me one moment. Let's see. Yeah, so I found some formulas for relative error and percent error, but I wasn't able to find anything for max error. Let's see. So for relative error, I found a formula that's let's see. So yeah, I guess it's kind of more of a science sense, but like relative error, it's measured minus real over this. Yeah, it's over real, and then the percent error we just multiply this by 100. So for this, it's going to be something about using the volume. So for the volume of a cube, if we have a cube of side length s, the volume of that cube is going to be v is equal to s cubed, right? And then to find these errors, we're going to need to differentiate both sides of this equation. So we're going to find basically dv ds. So we're going to take the derivative of this equation with respect to s. So dv ds should just be, if we differentiate the other side, 3s squared, something kind of like this. So from there, what we can do is we can multiply both sides by ds, right? And we'll get dv is equal to 3s squared times ds. So from there, we can say, so dv, it's kind of like an infinitesimally small change in v. Same thing with ds. We can kind of replace those d's with deltas. That's kind of the idea here. So if we have some change in side length, some uncertainty in side length, it's going to be related to our uncertainty in volume by this. Right, so from here, what we can do is we can take, let's see, I believe we can take this to be S and this to be delta S. This is 0.1. And then if we plug these into the formula, it should give us our change in volume. So delta V should be 3 and then 30 squared times 0.1. Let's see. And then I believe 30 squared is, what is that, 9,000 times 3 times 0.1. And then from there, we should just get, what is that, 2,700, I believe. Oh, that's too many zeros. All right, so does this look somewhat familiar? Hopefully.
Yeah.
Yeah. So now we just need to interpret what this delta V is. So this delta V is going to be our uncertainty in volume. So I think this may correspond to maximum possible error. Let me double check the answer key and see if it corresponds to something else. Sorry about that. Let's see. So, Oh, looks like we're off by a factor of 10. Hmm. Wait, it looks like they got the relative error for just for that. Let's see. Oh, I think I may have actually needed to plug in. I think I may have needed to plug in the what is it? The 0.1 into the first one instead. So right here. So let's see. Or something like that. Let me see really quick. So if it's 0.1 centimeters, 30 centimeters. That's strange. And because we have the 0.1 here. Yeah, because they're getting a factor of 0.01 somewhere. So I wonder if maybe they're plugging in the 0.01 for S instead of delta S. Maybe I have those backwards. Let's see. Yeah. Again, sorry about this. Really wish I would have been able to prep for this. Let's see. Yeah, because if you were to plug that in, then that would give, I believe if you were to plug that in, it would give the right answer because you would have, let's see. Or no, you'd be off by a few decimal places because you'd have 90 times 0.01. Maybe I just evaluated this incorrectly. Yeah, let me pull up a calculator really quick and double check.
Shouldn't 30 squared just be 900?
That might be it. Hopefully it is. Yeah, it is. So sorry about that. That would make a lot more sense. There we go. Thank you for that. 900. So then we just get the 270. All right. Cool. Yeah, so sorry about that little mental math mistake there. So we get 270 centimeters cubed. So that's going to correspond to our maximum possible error. Max possible error. Yeah, and then also you can forget this formula isn't really that relevant here in this case. So well, actually, I guess it might be. So let's see here. So so this is going to be the maximum possible error. So I think if I'm interpreting this correctly, we could say that this 270 is going to be our maximum measured minus real. Let's see, I'm trying to, so we have 270. And if we had a cube of exactly 30 centimeters, then the volume would be 30 cubed if it was exactly 30 centimeters. And I'm going to do that in a calculator so I don't mess up the math again. And that turns out to be 2,700. So then, yeah, our measured minus real, or our kind of like maximum possible error, like difference between the measured and the real with this percent error in measurement, it's going to be this, and then we can divide by this, or expected value if we were exactly precisely at 30 should just be this. And then if you do that division, we get 0.01, and that should be your relative error. And then from there, we just take this and multiply by 100. So yeah, I was actually, this formula did actually end up working out. So, and to find the percent error, just multiply by 100% to get the 1%. Yeah, so sorry about that. Kind of had to refresh on that. But yeah, any questions on this one before we move on? I'll label that as percent error.
No questions.
All right, cool. So in that case, we can move on to number 6. All right, so number 6, Strontium 90 has a half-life of 28 days. I'm going to note that is T sub 1/2, 28 days. So a sample has a mass of 100 milligrams initially. Find the mass that remains after T days. So we know that, I guess, let's see. So we have this much initially and find the mass that remains after T days. So do you guys have any ideas on maybe what sort of equation we could use to model this data?
We have the initial mass times e to the power of kt.
Yeah, exactly. It's going to be, I guess, because there's a couple different variables people use. Sometimes people use a or n, but it's a of t is equal to a. Oh, that's not an a. Oh my gosh, a not e to the kt. So something like this, right?
Yeah.
Yeah, where our a naught is going to be our initial mass, and then we have this half-life here. So we want to find just the generic equation in terms of t. So we want to find k. So we know that at t equals 28 days, a of t is going to be equal half our initial, right? Because that's the half-life. At that time, we should have half the amount of strontium 90 as when we started. So we can use these 2 bits of information to solve for k. All right, so we can just go ahead. So I'll plug in 1/2 a naught for a of t. Then we still have a naught over here. And then we have e to the k times 28 days. And then you could plug in a naught and then evaluate it from there, but you'll actually see here that they're going to cancel out because an a naught is non-zero. So those 2 values just cancel out. So we should just get 1/2 is equal to e to the k times 28. And then from here, we can just continue isolating for k by taking the natural log of both sides. These will cancel. We'll get natural log of 1/2 is equal to 28k. And remember, the 28 is in days. I've kind of gotten lazy with my units, but we'll have to make sure that we, when we get this k, it's going to be in terms of inverse days. So we'll have to, when we plug in times, we'll have to make sure we plug in terms of days. All right, and then finally, we'll get k is equal to natural log of 1/2 over 28. All right, could one of you plug it into your calculator and tell me what you get?
Negative 0.024.
Negative 0.024. That seems about right. Yeah, that's exactly what I got. Well, actually, I actually got minus 0.0247. So technically you'd round up to 0.025, but shouldn't make a huge difference. With these problems, typically I recommend if you're to go calculate values later, keep that same k in your calculator with all the decimal places, so you can just plug in the exact value there. But yeah, so in our case, I think it's fine just to round it off. It doesn't really give you a certain amount of decimal places it wants you to take k2, so I think this is fine. So now all we have to do is just plug everything back into our original equation, and we'll have our answer for our function. So our a of t should be equal to, so a naught was 100 milligrams times e, and then our k ended up being minus 0.025 to the t. And then if you wanted to put units, this is technically 100 milligrams, and then the k is technically inverse days. So days to the -1. because this 28 is in days and it's in the denominator. All right, so any questions on part A before we move on to part B?
No.
Cool. All right. And then for part B, super easy. All we have to do is plug in t equals 40 days to find the mass after 40 days. And I guess be careful here because sometimes they'll give you problems where time is in, say, years, and you have to convert to days because our k is in units of inverse days. So we have to plug in days to cancel that out to give us a unitless exponential in our e power. All right, so we're just going to find a of 40, which is going to be 100 times e to the minus 0.025 times 40. Plugging that into my calculator. Let's see, let me go ahead and do this. E to the answer, and then multiply that by 100. All right, as long as I haven't made a calculator error, this should be 37.1. It doesn't really give us decimal places, so I'll just go out 499 milligrams. This. All right, is that what you guys got? Do you have any, and also do you have any questions on this one? Rewrite that.
Yes, I got the same, and no, I don't have any questions.
Perfect. All right. Cool. I'll go ahead and double check both our answers, see if we are correct. Hopefully we are. Oh, it looks like they left it in exact form. Oh, and it looks like they did M of t instead of A of t. So yeah, and either way it should be fine there. So yeah, it looks like they left it in exact form here, where instead of getting k to some decimal places, they just left it in exact form like this and put that in the power. And then for m of 40, they just plugged in 40 and didn't even evaluate it from there, just left it in exact form. So that's definitely another way to do it as well. You could just leave it in this form here, in exact form. All right, cool. So you guys clear? Are you guys good if I clear this? Move on to number 7.
Yep, go for it.
Perfect. All right, so let's go ahead and clear this. One moment. Perfect. All right. So I scrolled up a little bit too far. 7. So we're going to use logarithmic differentiation to find the derivative of the function. So our function, let me write 7, y is equal to e to the minus x cosine squared x divided by x squared plus x plus 1. All right, so what's the first step in any logarithmic differentiation problem?
Multiply both sides with a natural log.
Close. I guess you could kind of think about it like that, but the real thing you're doing here is we're taking the natural log of both sides. So we're taking natural log of y, and we're saying that's equal to the natural log of all this stuff on the other side. Yeah, so it's something kind of like this. And the reason we do this is because now on the right-hand side, we can do a lot of nice algebraic simplification here. So we can say so natural log of y is equal to natural log of, so if you have I'll just do a couple, I'll just do a little aside for log rules. If we have the natural log of, say, a over b, this is equal to natural log a minus natural log b. And if we have natural log a times b, this is equal to natural log of a plus natural log of b. Another one of those cool natural log, or any, for that matter, any log base, any natural number should be good for that. All right, so up here I see I have multiplication, so I'm going to break that up right here. So we'll have natural log of e to the minus x plus natural log of cosine squared x. And then here we have a division, so that's going to be minus, and then we'll have natural log of x squared plus x plus 1 in the denominator. All right. So does that make sense there? All the algebra?
Yeah.
Cool. All right. So from here, what we can do is we'll just take the derivative. So we're going to differentiate each term doing implicit differentiation. So first thing, we'll look at our left-hand side. So the derivative of natural log y is going to be 1 over y times dy dx. And this is going to be equal to, so the derivative of natural log e to the minus x, that's going to be 1 over e to the minus x. Times the derivative of the inside is just going to be e to the minus x times minus 1. So the e to the minus x's are going to cancel out. I guess another way you could have done this is just canceling out the natural log and the e right away and just differentiating minus x, but either way, you should just get -1. And then for this next term, we have natural log of cosine squared x. So this is going to be plus, we'll have 1 over cosine squared x. And then from here, we need to differentiate. So it's kind of like a nested chain rule. Well, this is our natural log is our outer function. Cosine squared is our, x squared is our outer function, and then cosine is our innermost function. So doing the derivative of cosine squared, we're going to get multiply by 2 times cosine x, and then multiply by the inside, the derivative of the inside, which is minus sine x. And finally, we have this final term here, minus, and then taking the derivative of this, we'll get 1 over x squared plus x plus 1 times the derivative of the inside, which is going to be 2x plus 1. All right, cool. So we get dy dx times y is equal to, let's see, -1. One of the cosines here is going to cancel, and we'll be left with, what is that? 2 times minus sine x over x, and not over x, over cosine x, which is just 2 times minus 2 times tangent of x. So this whole term here will just simplify to minus 2 tangent x, and then minus 2x plus 1 over x squared plus x plus 1. And then from here, oh shoot, I messed up the left-hand side. Should have just left it as normal. This is 1 over y. To finish it off, we're just going to multiply both sides by y. So we'll get dy dx is equal to, so we'll have in parentheses -1 minus 2 tangent of x minus 2x plus 1 over x squared plus x plus 1 times our original y, which was this. So e to the minus x, cosine squared x, my bad, all divided by x squared plus x plus 1. And from there, the rest of simplifying is just algebra. So I think that's definitely going to be a good place to stop. Right there. And hopefully if I did all the derivatives and the algebra correctly, that should be what you should end up with. I think it's probably be pretty easy to check. So I'll just scroll down really quick. All right, it looks like they didn't do a simplification with sine over cosine being tangent, but either way, everything looks okay. All right, cool. So any questions on number 7?
Nope.
No.
Cool. All right, so let's see, we got about 13 minutes left. Let me go ahead and we can move on to number 8. Or I guess let me actually look at the rest because we're definitely not going to have time to do all of these. So how do you guys feel about linearization? Feel pretty good about it? Or do you want me to go over it?
Would you mind going over this one?
Oh, not at all, not at all. Yeah, so for linearization, we're first going to have to recall the formula. So the way I like to think about it is it's basically just that equation of a line that I was telling you guys about before, where we have y minus y1 is equal to m times x minus x1, except they rearranged it like this. And they're going to use some different variables. So instead of y, they're going to say this is L of x. And for m, it's going to be f prime. Let's see, I believe it's f prime at a. And then we have x, and in this case, our x1 is going to be a. And then our y1 is just going to be f at a, like this. So the y value is going to be our function evaluated at a. So that's how I like to remember this formula. So the first thing we're going to need to do is evaluate this derivative. So we need to find f prime of x. So this is our function. I'll do it over here. So f of x is equal to 1 plus x all to the minus 3. So taking the derivative, f prime of x, we're going to subtract 1 from our power and bring down the original. So we'll have minus 3, 1 plus x to the minus 4. And multiply by the derivative of the inside. But in this case, the derivative of the inside is just 1, so we don't need to write anything. So that should be f prime of x. And now, so we have a equals 0, and we're using it to approximate the number this. All right, cool. So a is equal to 0, so we need to find f of 0 and also f prime of 0. So f of 0, we plug in 0 to our original function. So we'll have 1 plus 0 all to the minus 3. That's just going to simplify it to 1 to the minus 3, which is just 1. 1 to any power is just 1. And for the next one, f prime of 0, we have minus 3, 1 plus 0 to the minus 4. This whole term goes to 1, so we should just get minus 3 on the outside. All right, cool. So this is our f of a, and this is our f prime of a. So we have L of x is equal to, so f prime of a is going to be minus 3. X minus a was just x minus 0 or just x. And then f at a, we calculated to be 1. So our full linearization should just be minus 3x plus 1. All right, so then now all we have to do is plug in our number that we're approximating, x, 1.1 to the minus 3. So we'll find L of 1.1 to the minus 3 power. This should just be equal to minus 3 times 1.1 to the minus 3 plus 1. Just like this. And I don't think that there's too much else there that we could simplify. I guess you could rewrite the 1.1 to the third to the minus 3 as minus 3 over 1.1 cubed, but that's not really going to make a huge difference there. So yeah, you could punch this into your calculator and get a decimal value, but I think this exact answer is perfectly fine. So any questions on number 8? I guess I never wrote that I was working on number 8. I kind of did it all over the place, but yeah, any questions on that?
Nope.
Cool. All right, so let's see. How do you guys feel about related rates? You want me to go over number 9?
Yeah.
I'm all right.
Oh, and yeah, so I'll do that. I'll just run through it really quick. So I'm going to go ahead and clear these drawings, and we can move on to number 9 just really quick. So radius of a sphere is increasing at this rate. How fast is the volume increasing when the diameter is this? This is something that trips even me up sometimes. So I like to rewrite this immediately. Radius is 40 millimeters, not 80, because the radius is 1/2 the diameter. So we have that, and we need to remember the radius of, not the radius, the volume of a sphere. And if you were to look this formula up, it's going to be 4/3 pi r cubed, like this. So that should be the volume of our sphere. All right, so then from here, with these sort of related rate problems, what we're going to want to do is we want to figure out the relation between the volume changing in time and the radius changing in time. And the way we can do that is with implicit differentiation, taking the derivative with respect to time on both sides. So doing it on the left-hand side, we'll just get dv dt. And on the right-hand side, we'll have, what is that, 4 pi r squared times dr dt. And then from here, we know, I guess I kind of skipped over this part. It's typically good to do this when you start off. We know that the radius is going to be 40 millimeters. We know that the dr dt, the rate that the radius is increasing in time, is going to be 4 millimeters per second. And we just don't know what the volume is. So we just want to figure out dv dt. So all we have to do now is just plug in r over here and plug in 4 for our dr dt. And we'll get dv dt is equal to 4 pi times our radius was 40 squared times 4. And then feel free to punch that in your calculator and simplify. But yeah, then this should be an okay answer. So it's just plugging in your calculator and simplifying from there. So yeah, any questions on that one?
No.
All right. Let's see. So, is there any one of the implicit differentiations that you'd like me to go over in particular? Because probably won't have time to go through all of them. So,
Could you go over number 2?
yeah, of course. All right, so I'm gonna go ahead and close this off. I'll switch colors one more time. So 10, 2. So we want to find dy dx by implicit differentiation, and then our equation we're given is e to the x over y is equal to x minus y. So with implicit differentiation, like I showed with the earlier rates, we're going to take the derivative of both sides, but in this case, it's going to be with respect to x, not with respect to time. So doing that on the left-hand side, if you have any exponential e to something, first thing you do when you take the derivative, rewrite it, e to the x over y, and we're going to multiply it by the derivative of the inside because of the chain rule. And for that, we're going to need to use the quotient rule. So we'll have, so the first term is going to be just y, because derivative of x is just 1 times the bottom is just y, minus the derivative of the bottom, dy dx, times x, all over y squared. And this is equal to 1 minus dy dx. All right. And then from here, what we're going to need to do is isolate for this dy dx. So to do that, what I'm going to do first is get rid of this denominator by multiplying both sides of this equation by y squared. And I'm also going to distribute this e to the y in here, and I'll distribute the y squared in here. So on the left-hand side, we should get y times e to the x over y. Let's see, minus dy dx times x e to the x over y is equal to y squared minus dy dx times y squared. And then I'll collect my dy dx terms on the left here by moving this over, and I'll move this guy over here to get that out of the way. So we'll have dy dx outside of y squared minus x times e to the x over y is equal to y squared minus y e to the x over y. I did the factoring out the dy dx all in one step. And then from there, we can divide both sides by the y squared minus e to the x over y and get dy dx is equal to y squared minus y e to the x over y, all divided by y squared minus x e to the x over y. And that should be your answer for that one. All right, any questions on 10.2?
No.
Cool. All right. I think I have time for about one more. I don't know. There was that one earlier, that one derivative that would be good to go over. So we could do that one. I think it was 412, or we could do another implicit differentiation, or we can do this last equation of the tangent line. Any preference on which one of those three that we do?
Can you do 412?
Yeah, of course. Yeah, but really quick before I do that, I'm just going to say these other two implicit differentiations should be kind of similar, except product rule instead of a quotient rule. And the equation of the tangent lines, number 11, is going to be similar to like the linearization and the other ones, where we do the where we have that equation, the y minus y1 equals m times x minus x1, and we find the m at that point and just plug in there. But yeah, with that said, let's go ahead and do 412. All right, so I'll switch colors one last time. So 412, shoot, let me get rid of that last thing. xii, perfect. So we have y is equal to 2 to the 3 to the 4 to the x, and we want to find y prime. So there's a couple different ways you can go about doing this, but the way that I find most intuitive is that I want to get these exponents down to the front because I don't like dealing with them just like this. So I'm going to take the natural log of this equation a few times. So first thing, I'm going to take the natural log of y is equal to the natural log of 2 to the 3 to the 4 to the x. And then from here, what I can notice is that we have 2 to the 3 to the 4 to the x. So this is our power, and this is our base. So I can bring this down to the front. So we know natural log of y is equal to 3 to the 4 to the x times natural log of 2. And then from here, we can do it again. So we can just take the natural log of both sides again. Natural log y is equal to, we'll have natural log 3 to the 4 to the x times natural log of 2. And then let's see. So from here, so we have natural log of y is equal to, so let's see, this is a multiplication. So I think, let's see. Yeah, because we can use our log rules and we can say this is natural log 3 to the 4 to the x plus, let's see, plus natural log of 2, I believe. And then from there, we can bring this power to the front, and then we can take the natural log just one more time. So it'll be something like this. And then we'll have natural log of y is equal to, so we'll have the natural log of 4x natural log of 3 plus, let's see here, natural log of 2. Huh. Man, another one that I wish I had time to prep for. Let's see. I am running out of time. Let me see what the answer looks like really quick, because I'm wondering if they did a different method than this. Oh, it looks like they did something similar here. I think it might be a property where, like, even though we have this multiplication here, we can still bring this power down. Shoot, let's see. Because we should end up with something where it's like natural log of y is equal to natural log of 2 times natural log of 3 times natural log of 4. And then we'll have, in the end, I think it's just an x, something kind of like that. Let me double check one more time. Let's see, so they end up getting, let's see, yeah. So let me, man, struggling with algebra last second. So natural log, so we brought down the 3 to the 4 to the x, so this came here. So if we were to just bring down the 4 to the x, yeah, it's strange because, yeah, let me look and see here. Yeah, give me one moment. Sorry for going over, by the way. Yeah, we'll finish up right after this problem. Give me one moment. Yeah, so I think another way you can do this that might be a bit better than just taking the natural log a ton of times. Well, let's see. Yeah, it would be to use the rule. Let's see, a to the b is equal to e to the b times the natural log of a. Like this, where it's kind of like what we're saying, well, we're taking e to the natural log of a to the b, where this is the same because the e to the natural log cancel out and we're bringing the b to the front. So if we apply that in this case, instead of just taking the natural log a bunch of times, we'll get y is equal to, let's see. So if we do this, and so in this case, our a is equal to 2 and our b is 3 to the 4 to the x. we'll get, let's see. So e to the power 3 to the 4 to the x times the natural log of 2. All right, so then from there, we want to differentiate this. So y prime is equal to, so the derivative of this with respect to x. Let's see, and then how could we evaluate this derivative now? So now from here, so we have the derivative of e to a power, right? So remember the first step with differentiating e to the power something, we're just going to rewrite that something. Oh shoot, let me actually scroll back down, make sure. Yeah, like that. And then we're going to rewrite e to that same power, right? So we'll have e to the 3, 4 to the x times all times the natural log of 2. So this is in parentheses times natural log of 2 all in our e. And then we'll have, let's see, and then we need to multiply by the derivative of this top function. So d by dx of 3 to the 4 to the x times natural log of 2. All right, and then from there, what we can do is something a little bit similar. So y equals e to the 3 to the 4 to the x times natural log of 2. But actually, we know that e to the 3 to the 4 to the x, that's just our starting function, right? That's just our a to the b. So that's just going to be 2 to the 3 to the 4 to the x. All right, and then from there, so we'll have d by dx of this thing. But we can bring this natural log of 2 is just a constant, so I'll bring that to the outside. So times natural log of 2. And then d by dx of this. But this, we can do the same thing. We can use the same rule where a to the b is equal to e to the b natural log of a. So we'll have, in this case, our, so we have 3 to the 4 to the x. Our a is equal to 3, and our b is equal to 4 to the x now. So we'll have d by dx e to the, let's see, b is 4 to the x times the natural log of a, which is 3. All right, so now we can just go ahead and differentiate this next part again. So we'll have y prime is equal to 2 to the 3 to the 4 to the x times natural log of 2 times the derivative of this. We're going to do the same thing. Rewrite it e to the 4x times natural log, natural log of 3. Let me actually go ahead and do that really quick. And then from here, we need to differentiate the inside d by dx of 40x times natural log of 3. And then I'll come over here. I'll come all the way up over here so we have some more room. So y prime is equal to 2 to the 3 to the 4 to the x times natural log of 2, factoring out these. And then we'll have this, which is just, what is that? 3 to the 4 to the x. And then I'll multiply that by natural log of 3. And then finally, we're just taking the derivative of 4 to the power x. And then if we use this same rule here, where a is 4, b is just x now, we'll have derivative of e to the power x times natural log of 4, which is just going to be e to the x natural log of 4 times natural log 4, or 4 to the x times natural log of 4. So we'll finally just multiply by 4x times the natural log of 4. Cleaning this up a little bit, we'll get y prime is equal to 2 to the 3 to the 4 to the x times 3 to the 4 to the x times 4 to the x times natural log of 2 times natural log of 3 times the natural log of 4. And fingers crossed, I did all of that algebra correctly. I'm going to double check really quick, and then we can end off here. All right. Any questions on that one? That one's a doozy. There was a similar problem that I was doing for the other review sheet that this worked out for, but in this case it actually didn't, and we had to use a slightly different exponent rule there. Yeah. So any questions on this one before we end off?
No.
yeah, so again, sorry for going over. That was definitely a doozy. Yeah, make sure to get enough sleep before your exam, get a nice meal beforehand. And yeah, like I said, sorry about not being as prepared as I would have liked to for this review. But yeah, have a great day. And yeah, this should be uploaded on YouTube in a little bit. So yeah.
Thank you. Have a good rest of your night.
You too.
Thank you.